Can James Webb find planets at Alpha Centauri? Does it make sense to build a lunar elevator? And what would I want if I had no funding limitations? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I will gather them up and I will answer them here. Now, just a reminder, we do the show live every Monday at 5 p.m. Pacific time. So obviously you can watch the show after, but if you want the true live experience, come join the live show, ask your questions in real time, chat with other people. I stick around for like another hour after the show that you're watching here. So it's a good time. That's Monday at 5 p.m. Pacific. All right, let's get into the questions. Duke G1848. How is it more easy for Webb to observe the TRAPPIST-1 system than Alpha Centauri, Proxima Centauri? The TRAPPIST-1 system is one of the most exciting planetary systems that astronomers have found so far. You've got this red dwarf star, which is a bit of a problem, with 6 Earth-sized worlds orbiting around it, 3 of which are in the habitable zone. The 2 closest ones are too close to the star. The next 3 are in the habitable zone, and then you've got 1 more on the outside of that. It is like the perfect star system for a telescope like Webb to observe it. And in fact, Webb has already observed 2 of the planets. It's probably observed more, but the science results are out for 2 of them. And so far, the 2 inner planets are dead super Mercuries. But the question you're asking is like, why would we look at this star that is dozens of light years away, that is a red dwarf, that is, probably not great to its planets, when we've got Alpha Centauri right next door, and you've got 2 stars that are similar to the sun in a binary system? They could have planets there. Yes, they could, but the problem is that the coronagraph on James Webb just is not powerful enough, or doesn't block enough of the light for you to be able to distinguish any planets orbiting around Alpha Centauri. Like, astronomers still don't know if there are planets orbiting around Alpha Centauri. So the coronagraph on James Webb, which is designed to block the light from the star so that it can reveal any planets nearby, is only able to resolve the difference when the difference in brightness between the star and its planets isn't that great. And that's what you get with a red dwarf star. So it can see the TRAPPIST-1s, but it just can't see any planets at all around sun-like stars. The plan is that the Nancy Grace Roman telescope that's coming out in 2027, it's going to have a coronagraph on board that is capable of distinguishing between the light of a star and its planets by a factor of 100 million. So in other words, you can have a star that is 100 million times brighter than the planet and still be able to block the light from the star to be able to see the planet. And what that'll get you is Jupiter-sized worlds orbiting around sun-like stars, which is, that's not the Earth-sized world. That's what we really want, but that gets you close. So then the next one that you want is you really want the Earth-sized world orbiting around a sun-like star. And that's the kind of thing you'd want to be able to see around Alpha Centauri, around either one of the stars at Alpha Centauri, or maybe orbiting around both. And so the telescope that's going to be doing that is called the Habitable Worlds Observatory. And you probably remember LUVOIR, and HABEX. Well, LUVOIR and HABEX got merged together, and they're getting mashed into this new telescope that is going to have the same size as James Webb, but it's going to be specifically designed to search for these Earth-sized worlds orbiting around sun-like stars. And it's going to have a coronagraph that is capable of a 10 billion times light distinction. So you could have the star and 1/10 billionth of the light, and that's the planet, and you would be able to observe the planet separately, directly. So you're not measuring the brightness of the star as the planet passes in front. You're not measuring the radial velocity of the star. It's moving back and forth. You are literally measuring the planet, which is beside the star. But that's going to take a few more engineering feats to go from what's going to be going into the Nancy Grace Roman telescope. It's going to go into the Habitable Worlds Observatory. Now, the question that I sort of didn't answer yet was, why aren't they going to go after Proxima Centauri? And Proxima Centauri, that is the closest star to the sun, and it is a red dwarf star, just like the TRAPPIST-1 system. And the answer is, I don't know. I haven't seen any observations made of Proxima Centauri yet. It is a red dwarf star, so theoretically they could do it, but it's a lot less known than the TRAPPIST-1 system, and so it was a lower priority, I guess, to try and search for. And yet it is the, like, it's right next door, and so I'm sure that it is the kind of star, the kind of planet that they will eventually task James Webb to. Now, when it comes to planets around Alpha Centauri, there is a plan in the works to observe planets around Alpha Centauri. So there's a new spacecraft that's being built, and it's actually fairly small and has just one job. It's called Ptolemy. And its job, and this is so clever, is that it is going to watch the movement of the two stars of Alpha Centauri as they orbit around each other. It's going to focus on one star and then watch the orbit of the other star. And if that other star has any slight variations in its journey around the other star, it's going to be able to measure the presence of a planet around Alpha Centauri. And then it's going to be able to look at the other star in the Alpha Centauri system and then measure any slight variations moving back of that star and be able to tell whether or not Alpha Centauri has planets. So James Webb just couldn't do it. We need to wait for, Nancy Grace Roman could find Jupiters, but it can't find Earths. But the Ptolemy spacecraft, which should be launching very soon, will be able to find Earth-sized worlds orbiting around Alpha Centauri. So not sure why they haven't gone after Proxima Centauri. James Webb can't do Alpha Centauri, but there are telescopes coming that will be able to do it. I'm sure you've noticed the Star Trek planet name that's appeared above my shoulder, and this is a way for you to vote on the questions that you thought was the best. So we're going to list a different planetary name all the way through the show. Just wait to the end. We put a list in the show notes, and then just write down the one that you thought was the best. We'll count them up, and we will celebrate. Now, it's been a couple of weeks since we've done one of these, but the last time we did was Liam for what is the next big space telescope scheduled to launch. And I answered the question in that question show. So thank you everybody who voted on that question. Thank you to Liam for asking the question. All right, don't forget to vote. Farron N, can you talk about a lunar elevator? Is the concept theoretically possible? Would it be impossible if the moon and Earth were not tidally locked, since the dismount site would keep rotating? So people have talked a lot about space elevators, and this is the idea that, if you build a tower that is tall enough from the surface of the Earth, you could step off into geosynchronous orbit. And so you would climb up this big long ladder, and you get to the top of the ladder, and then you would be at geostationary orbit, where the same part of the Earth, you would essentially be turning around the Earth at the same speed that the Earth rotates. And so you would be in orbit, and all you had to do was climb a really tall ladder. And so the more practical engineering version of this is called a space elevator. And so what you do instead, though, you can't have a ladder because the ladder will just fall down. So you need to have a tether that is strong enough to be able to hold itself together so that the end that it's reaching the Earth is just touching the Earth, and then it's able to hold itself together. And then what you do is for it to be completely balanced, you need to then go the distance from the Earth to geostationary orbit again away. So you go double the distance to geostationary orbit. And that gets you this big, long elevator thing that's just hovering in place. Now you can shorten the part that's beyond geostationary orbit by putting a mass. You can bring an asteroid in, you put it into geostationary orbit, you tether the asteroid to this, and then you've got this space elevator. And then you could get on your elevator, you could go all the way up to geostationary orbit, get off, and now you can escape Earth's gravity without needing a rocket. And for the longest time, people were absolutely sure that this was going to be the way, that this could bring the cost of getting to space below $1,000 a kilogram, maybe to $100 a kilogram. But there's a ton of downsides, like a space elevator requires electricity to be able to carry your payload up to the top to geostationary orbit. It's going to take you multiple weeks. Only one payload can be on the tether at one time. It's a minuscule amount of cargo that you can actually carry. And as SpaceX started to work on this idea of a two-stage reusable rocket, Starship, then suddenly you've got this system that could carry payloads into space for less than $100 per kilogram. And now suddenly a space elevator just doesn't seem cost effective. And just imagine the flexibility of having a fully reusable two-stage rocket. So the idea of a space elevator has taken a bit of a backseat here on Earth. But the place where it does make a lot of sense is on the moon. And that's because the gravity on the moon is 1/5 what it is on the surface of the Earth. And so you need a much less strong cable. Theoretically, you could use carbon nanotubes formed into this giant cable, and it could just barely theoretically hold itself together, but we haven't been able to make carbon nanotubes longer than a couple of centimeters. So to build one that is 36,000 kilometers long, that is a challenge. But if you want to build a space elevator on the moon, then you just need something like Kevlar. Like, there are plenty of fabrics that have been designed that would work perfectly. And so what you do with the moon is you go from the surface of the moon to the Moon Earth L1 Lagrange point. So that's the one, we snuck in a Lagrange point question. So that's the one that's in between the Earth and the moon. And I forget the exact distance to it. It's, like a few tens of thousands of kilometers above the surface of the moon, but you really just need a string of Kevlar, spectra, like some kind of composite material to be able to make this journey down. And then you can absolutely raise payloads from the surface of the moon, get them to the L1 Lagrange point where they're no longer trapped in the moon's gravity, and you've got this point where they can then drift off into the rest of the solar system. And so I've seen a lot of interesting proposals, a NIAC grant, in fact, that went into the details of what it would take to build a elevator on the moon, and what is just science fiction for Earth is borderline practical for the moon. And so you can imagine in the far, far future, when we start building the O'Neill cylinders at the Earth's L4, L5 Lagrange points, there could be lunar elevators operating on the surface of the moon. They're carrying all of this regolith up from the surface of the moon and feeding them out to the O'Neill cylinders for that future life in giant space habitats orbiting Earth. Daniel Zussman: if you had to choose and make up your own mission as of today with no funding limitations, what would it be? Well, like, no funding limitations, that's really hard to constrain myself, because then all kinds of things. So let me mention a couple of technologies that I'm really interested in, and hopefully we can kind of bring them together. So the first technology that I'm really excited about is, or not even a technology, but it's the solar gravitational lens. So this is this place, it's about 1,000 astronomical units away from the sun. And if you put a telescope into the solar gravitational lens, then you get a magnification factor of about 30,000, thanks to the gravitational power of the sun acting like a natural lens. And so you could, for example, if you put like a 1 meter telescope into the solar gravitational lens, you could observe an exoplanet with a 1,000 pixel by 1,000 pixel image of an Earth-sized world orbiting around a sun-like star. Now, you only get to choose one. Like, each spacecraft can only see one planet, but you could see oceans and weather and even city lights, and it wouldn't require a very big telescope. So, and I've done a ton of interviews and videos about the solar gravitational lens, so you can look into that. The second thing that I'm really excited about is space-based assembly of telescopes. So, like, when we looked at James Webb, you had this origami to be able to get the telescope up into space, and it's at the very limits of what fits within the fairing, the standard fairing on the Ariane 5 rocket, 5 meters across. That's fine. And like, even Starship maybe is going to give you a 9 meter fairing. You could put a much bigger telescope into a 9 meter fairing, but you're still limited, and you're still going to have to do some origami to make this thing fold up and be inside the fairing of Starship. No, you want to build a space telescope in the way that you would build the International Space Station, in bits and pieces. And so there's a really great proposal that's been sort of roaming around NASA for a few years. And I think, this is going to be the future of big space telescopes, and that is going to be space-based assembly. So you send up the bus, which is like a little smart box with Canadarms attached to it. And then it hangs out at the L2 point waiting for more. And then you send it the propulsion module, and then you send it solar panels, and it's got these little robotic arms, and it just starts assembling itself as a space telescope. And eventually you send it bits and pieces of the primary mirror, and then you send it bits and pieces of the secondary mirror, and it's able to then assemble all this stuff together into a giant space telescope that is much bigger than anything that could be launched onto a rocket. And so right now, James Webb is 6.5 meters. The Habitable Worlds Observatory is also going to be 6.5 meters. Like, it's going to be a while before we get 20, 30, 50 meter telescopes, but bigger is better. And then the last technology that I'm really excited about is interferometry, and that's where you combine the light from multiple telescopes that are separated by a distance to act like a virtual telescope of the gap between the telescopes. And so if you put one telescope and then you put another telescope 100 meters away and you align them perfectly in space, which you can do, then you have a telescope that is 100 meters across. At least it has the resolution of 100 meters across. It's very complicated, but anyway, it's the equivalent of a telescope that is 100 meters across for certain kinds of work that you want to do. And now let's put it all together, right? Let's build space-assembled telescopes that are acting in an interferometer, and let's put them to the solar gravitational lens. Can you imagine what we could see? Like, we could watch aliens reading newspapers. So that's what I want. Yes, please. No limit on the funding. Platybium obtusiangulum. Any update on the James Webb observations for TRAPPIST-1 and the outer planets possibly having atmospheres, please? So as of this recording in early January, there is no official announcement of any observations made of the planets of the TRAPPIST-1 system. So we've got TRAPPIST-B, TRAPPIST-1c. They are airless supermercuries. We have no information on any of the others. It's assumed that the observations have been made on TRAPPIST-1d, and that's going to be that first planet in the habitable zone, and maybe even E and F. So the fact that we haven't heard anything there's like two possibilities. One is they have found no atmospheres around the planet, and they are just really working hard to confirm it. Like, when we got the first announcement of a lack of atmosphere on TRAPPIST-1b, we got like one press release that came out, and then a couple of months later we got another version of that where another team of astronomers had done a more detailed analysis of the atmosphere of that planet and confirmed, yes, indeed, there is no atmosphere around that world. So that's the one possibility. And then the other possibility is that they did find an atmosphere, and everyone is waiting for this science result. And so they've got to be absolutely sure. They've got to have all of their I's dotted, T's crossed, that everybody is going to tear apart this analysis and make absolutely certain. But, the data have been gathered, and at a certain point, the time is going to run out for the team that requested the time on James Webb, and it's going to become open access, and anybody who wants is going to be able to get into that data, look at it, and be able to figure out what's going on around that world. But, I've been obsessed about observing exoplanetary atmospheres for the last couple of months, and I've done just a series of interviews, and sort of my most recent interview was with Dr. Louise Wellbanks, and we talked quite a bit about what's being done with James Webb to observe planets around red dwarf stars. And his feeling is that these planets are awful, and that we've got, like, over the next couple of years, it's just going to become more and more obvious that they're not a place to look for atmospheres, that the stars themselves have such killer flares, the planets are orbiting so closely to the star that they're just battered by all of the radiation that's coming off the star, all of the giant flares, that it's just too inhospitable for even an atmosphere, not to mention life. And so that means that we're going to have to shift away from hoping that these red dwarf stars are places to look, and we're going to need better equipment to be able to see Earth-sized worlds orbiting around, say, K-dwarfs or dwarves, or like stars like our sun. And so we're in this sort of hopeful phase right now, and I'm now preparing myself emotionally for the possibility that red dwarf stars are not going to be a place to search for atmospheres. And people will keep trying, but if we turn up 20, 30, 40 planets around red dwarf stars that in the habitable zone that don't have atmospheres, then we'll get to a point where we're like, okay, we need a new strategy. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version, that extra hour that I mentioned? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Graham Keatley, Jim Pizarris, David Nagrevsky, Terry Barker, Ross Kennedy, Greg Goodson, Jerry Conant, Shane Johnson, Stephen Ryan, and Stacy Stewart. Join the club at patreon.com/universetoday. Alexander Stainton, are there any talks about making a multi-unit telescope the size of the inner solar system or larger? Yeah, I've actually done an interview about this. I've reported on this a few times. We've report on this a lot on Universe Today. There is a strategy to build an interferometer, which is like the Event Horizon Telescope, but one that would be the size of the Earth's orbit. So you would put one telescope at the Earth-Sun L4 Lagrange point, you put one at the L5 point, and one at the L3 point. That's the one on the opposite side of the sun. And then the three telescopes would form this giant equilateral triangle, and you would get a telescope that is the size of the orbit of the Earth. And that sounds great. Like, that sounds like okay, we've got a telescope that is the size of Earth's orbit, but it is a radio telescope. So it's going to be able to make the kinds of observations that the Event Horizon Telescope can make. The event horizons of supermassive black holes, other objects like that. Things in the radio spectrum. Although they are able to be a rough equilateral triangle, they're not a perfect triangle. Like, they're going to have to be shifting around. You're not going to have that level of precision that you want. And there's certain kinds of observations that they can make that are better or worse than other ones. Once you move into like visible light, which would be really cool, like to have a telescope that's that big, then we just don't have the technology to be able to align that. The closest thing that's going to be happening is you've got the LISA interferometer, which is a gravitational wave observatory that's being built by the European Space Agency. It's going to put its three spacecraft tens of thousands of kilometers away from each other, and they're going to be communicating with lasers, going to remain in perfect position, forming this kind of equilateral triangle that's going to be orbiting just outside the Earth. And they're going to be detecting gravitational waves that are beyond the capabilities of existing gravitational wave observatories. So that's all that's sort of planned, either concretely or sort of roughly right now. But no, like the future of like a giant telescope, a visible light telescope that is the size of the orbit of planet Earth, that would be fantastic. Yes, please. B. Michael Neal. Catching up to the Voyagers to either resupply power or destroy them for reasons of confirmed alien threats. Is the trip possible? What say you? So is it possible to catch up with the Voyagers? Yes. There's a mission plan that keeps going around for trying to catch up with Oumuamua, which is this interstellar object that's on a trajectory that's going to take it outside of the solar system. And the plans are like, if you worked on it immediately today and you built this tiny little spacecraft and you attached it to the top of a Falcon Heavy rocket and you launched it tomorrow, then you could catch up with Oumuamua in 20 or 30 years. And then you can make some observations, you could beam them home, we could learn a little bit more about an interstellar object. So in theory, you could do the same thing, which is that you could build some kind of rescue spacecraft, build it really quickly, attach it on top of, I don't know, like instead of the next Artemis mission going to the moon, you have it instead launch the rescue spacecraft to the Voyagers. And away it goes off to see the Voyagers. And it maybe takes 20 or 30 years. Now, I mean, the Voyagers are much farther away than Oumuamua is. So maybe you need 50 years, 100 years to catch up with the Voyagers. So your rescue spacecraft is going to need a rescue spacecraft after a while if you actually catch up with it. And you're going to have to do all of these, gravitational slingshot flybys to get out there. To bring it home is next level. Now, there was a proposal that I sort of did an interview with someone about, where they proposed that you could actually grab a sample from Oumuamua, and the sort of the amount of change of velocity is like a couple of 100 kilometers per second in total delta V to actually be able to grab a sample from Oumuamua. And their proposal is that you take the kind of reactor that is on board Curiosity, Perseverance, and you sort of scale it up a little bit, and then you just bolt on an ion engine onto it. And so it's providing electricity, it's got the ion engine, there's like nothing else, maybe a little grabber arm to grab a sample, and then you send it on its way on top of Artemis, on top of the SLS. And so you send an SLS with this super efficient ion engine powered by a thermoelectric, radiative thermoelectric generator. And you could get those kinds of delta Vs, enough to catch up with Oumuamua, grab a sample, bring it home. And I guess you could attempt to rendezvous with one of the Voyagers and then bring it home. Now, the problem, of course, is that the Voyagers are almost dead. And so they're communicating right now, and they're telling us what their location is. But in another 10 years, they're going to not have enough power to even be able to have their transmitters sending information back home. And so you've built this rocket, you sent this mission, it's on its way to chase up the Voyagers, and then they go dark. And space is big, and so you have to figure out where they are, and that's probably impossible. Like, you could know where they are within a few tens of thousands of kilometers, but it's really hard to then zero in. But maybe you could do it. Maybe your spacecraft has a telescope on board and you could find it, and then to try to change the speed of that spacecraft and to bring it home. Like, if all of humanity put all of its energy and the gross domestic product of everybody into bringing home a Voyager and putting it in a museum, I think we could pull it off. So, but is that is that the best use of all of our money? Probably not. Lily Rose, is Artemis 2 going to the moon or just doing a flyby, and what experiments and tests will they be doing on the mission? Yeah, so Artemis 2 is going to be a flyby of the moon, and the closest analogy of that was the Apollo 8 mission that went before they actually started to land humans on the moon. They had some astronauts on board, they did a flyby of the moon, and then they came back to Earth. And the orbit that they chose is one that gives you a free return trajectory, that you're able to go to the moon, and if anything goes wrong with your spacecraft, you're able to then return back home, and you don't need power to be able to do that. And so with Artemis 1, they took this very special trajectory where they went around the moon, then they burned their rocket again, and they sort of went really far away from the moon, and they fell back down to the moon, and they went around the moon again, and then they came back down to Earth. And with Artemis 2, they're going to do a much simpler trajectory that's going to give them that free return option in the way that they had with the Apollo 8. This time there's going to be 4 astronauts on board, including a Canadian, which is awesome. And they're going to do a flyby of the moon. And they have no landing system. And so what is the goal? Well, the goal is to prove that the SLS is capable of launching human beings to the moon. The goal is to test whether or not the Orion capsule can keep 4 human beings alive in space for the duration of a mission to the moon. And these are all important things to know. And so even though it might not be the mission that we really want to get right to, sometimes you got to do the intermediate test first. So yeah, they're going to test out how well does its propulsion system work for this kind of a mission? How well does its energy systems, its power, its heat radiation, are there any, what kinds of supplies are the astronauts going through? Are they, how much water, how much air, how much, all that kind of stuff are they needing? Because the Orion is built as a deep space vehicle. It's designed to keep human beings alive away from low Earth orbit, which, we had the Apollo missions, but really there hasn't been anything since then that's designed to pull this off. And so Orion is back to keeping humans alive in deep space. And there's just a giant checklist of things to mark. Now, right now, the plan is to launch Artemis 2 in November 2024. I haven't heard of any delays, so I think that's all still go. And so within less than a year, we should see that next mission fly off to the moon, which is pretty cool. on the land. In our solar system, don't underground oceans appear to dominate? Why couldn't there be oceans on other red dwarfs as a source for life? For sure. It's believed that there are dozens of times as many water worlds in the solar system than there are terrestrial planets that could have life on their surface. I mean, we've got Earth for sure, maybe Mars, maybe the upper atmosphere of Venus, and that's it. And yet we know that we've got all of the ice moons of Jupiter, several of the moons of Saturn, the moons of Uranus, the moons of Neptune, Pluto itself, its moon, and then all of those Kuiper Belt objects, and who knows what else is out there in the Oort cloud. There are likely hundreds of places in the solar system that could have life under a thick sheet of ice with a liquid ocean underneath. That's some kind of like hydrothermic activity is supplying the energy for microbes or whatever. And so if you had a planet that was farther away from its star, and so it's no longer in the habitable zone, and so its surface is frozen, you could absolutely imagine it withstanding flare after flare after flare from the star, no problem. Like, if you go out into space, you're going to receive a lethal dose of radiation if you're out there long enough. You're going to get hit by solar storms. You're going to get hit by cosmic radiation. It's a bad day. But if you can put 1 meter of ice or water between you and space, that problem goes away. And so if you're under tens or hundreds of kilometers of ice, then you're safe. You're perfectly safe. And so all those problems of flare stars, of red dwarf stars that are letting off all of this energy, not your problem. But how do we find that? How do we discover that? How do we observe that? How do we detect the chemicals coming from those worlds? If there is life on Europa or life on Enceladus, like, we're having a really hard time even making those kinds of observations, and those places are right here with us in the solar system. I can't imagine any way that we could confirm the presence of life on an ice planet that is orbiting around a red dwarf star. Now, if we do find life on Europa and Enceladus and Pluto and all these places around the solar system, then the obvious question is going to be, if we're finding these ice worlds around other stars, is there life there? And the answer has got to be, well, we don't know. We don't have any data for that. And so this is the irony, is that chances are there are thousands of times more worlds. When you think about all the rogue planets orbiting around in the Milky Way, there are thousands of times more worlds in the Milky Way that are potentially habitable but are under ice than terrestrial planets like Earth. And yet, these are the only ones that we have a shot at finding any life on, and not the ice worlds. R.D. Matheson. Hey Fraser, if Betelgeuse does go supernova, will the Earth receive an initial preceding neutrino burst? And if it does, how long will it be? Yeah, so when a very massive star like Betelgeuse dies, it will have this implosion where all these outer layers will collapse down, and then it will bounce off of the center, and you'll get the formation of a neutron star or a black hole, and then you get the supernova, where now all of this material has piled up an enormous amount of pressure and energy, and then it explodes. And we will see this flash in the sky as the star is exploding. But the thing that we'll actually learn about first are the neutrinos. The neutrinos are able to escape the star before the actual energy of the star. And that sounds weird because neutrinos move slower than the speed of light. And so you would expect the light would come first and then the neutrinos. The problem is that the light is trapped. The radiation that is inside the star is trapped inside all of that matter. And when you think about the light that's formed inside the sun, it has to random walk its way out of the sun. It can take 50,000 years more for light, for photons that were created through fusion at the center of the star to finally reach the surface of the star. And then they just jump out into space. And so you've got a similar process. You've got this supernova that is collapsing down. The energy is being trapped inside. But neutrinos are free to move. They don't need to worry about all of that material. They can move through a light year of lead, no problem. And so all of the neutrinos escape immediately when they're formed in the supernova explosion. And so the thought is that we will get a burst of neutrinos here on Earth minutes, maybe hours before we see the visible light of the supernova. And so astronomers have developed a supernova warning network where they've got these neutrino observatories here on Earth that are designed, if they detect a burst of neutrinos coming from relatively nearby, and you have to be within a few hundred light years of Earth, then they'll send out this big alert announcement, and then astronomers will scan the sky hoping to see the supernova. There's only a couple of candidates that this would be for. The Chinese are working on a new system. They're going to build their own version of a neutrino detector warning system that, same thing, should give you, a warning within a few hundred light years, maybe a few thousand light years of Earth, and then a one that does the neutrino observations as a follow-up out to essentially within the Milky Way. And so hopefully we'll be able to tie those neutrinos to the supernova more closely. Like astronomers have detected the neutrinos that came from supernova 1987A. They just didn't realize that's where they were coming from. They detected additional neutrinos coming through their neutrino observatory, and then after a while, after really hard work, they were able to tie them to that supernova. And so in the future, though, they'll try and turn this into an alert system so that, like imagine a supernova goes off, a burst of neutrinos is sent in our location, we are able to, with multiple observatories, triangulate where that supernova is, we turn our telescopes at it, we focused our gravitational wave observatories, and then right on schedule, the supernova appears and you get to see the star that was there before, the entire unfolding explosion, and then track the aftermath over the coming weeks and months and years. So it's a great idea. It's just like right now they need to be relatively close to be able to see it. All right, those are all the questions that we had this week. Thank you, everyone, for asking the questions in the YouTube comments. Thanks for everyone who joined the show. It was super fun. It was great to be back after not doing this for a week. Apparently, my brain still works, so that was good. Go ahead and vote if you haven't already, and tell us what you thought was the best question. I'm going to talk about the 2024 eclipse in a second, but first, I'd like to thank our patrons. Thanks to Hey Twilight, Dougie Stewart, Stephen Krasaki, David Richards, Mark Ansis, Joel Yancey, Antonio Lofi-Lara, Dustin Cable, Vlad Chiplin, Modzo, George, David Giltanan, Andrew Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. In this week's Space Bite, I talked about how you can see an aurora, and we're entering solar maximum, and this is a great time to try and see an aurora. Get an aurora app alert on your phone, and you can hear when the next aurora is going to happen, and hopefully you'll get a chance to see it. But the other big event that's happening this year is to see a total solar eclipse, and that's going to happen on April 8th, 2024. And for those of you who remember, we saw a total solar eclipse back in 2017, and I was near St. Louis, and unfortunately, we were clouded out for the sort of totality of the eclipse. And so I didn't get a chance to see it, but I saw parts of it. And so now I'm going to see it again. And if you haven't already, total solar eclipses are one of these events that are just, there's nothing else like it. And you've got to get this into your brain. And so this eclipse is going to happen. It's going to go from Mexico through the United States, going to go through Austin, Dallas, up through Canada, near Ottawa, and then sort of up into the Arctic. And so if you live reasonably close to any of those locations, really think about how you're going to get a chance to actually see this eclipse. A partial solar eclipse is not good enough. A 99%, so like if you're at like a 70% solar eclipse and you're like, oh, should I just drive so I can get to a 90% solar eclipse? No, you should not. It's not worth it. But if you're at any partial solar eclipse and you want to get to totality, you should absolutely do it. And it is experience like nothing you've ever had. The sky turns into this weird twilight in all directions. All of the animals, the birds are suddenly quiet all around you. And the sun, which has been like really bright, just gets completely obscured by the moon. And then you get this really faint solar corona that, the atmosphere of the sun is easy to see. And, we're approaching solar maximum. And so we're going to see probably more activity in the corona than we normally do. It's amazing. It's amazing. And so don't commit. And yes, there could be clouds. And yes, there's going to be crowds. And yes, it's going to be hard and expensive. But if you can, try to see this eclipse. And if you do, you're going to be hooked. And then you'll become these eclipse chasers that travel around the world trying to get as many eclipses into their eyeballs as they can. All right. I've got my flights planned. Hopefully you will too. All right. We'll see you next week.